All right, I love this one. So today we're going to be proving one of Kepler's laws, and he came up with this back in the late 1500s. Uh, Humanity science, they had figured out that like the Earth wasn't at the center of the solar system, that the sun was at the center of the solar system, and that planets were orbiting it. And so Copernicus had already done that, and after that. Kepler was looking at this, and Kepler was a very, very religious man, and decided he believed firmly that the orbits of the planets around the sun would be in some divine and beautiful ratio, and he was looking for that beauty in nature. And he had this idea that he worked on for many years of trying to put the orbits of each planet around the sun in this pattern of three-dimensional perfect shapes, right, with perfect spheres in between each one, and these hollow cubes, and I think that's a tetrahedron is what that's called. I might have that wrong, but all of these perfect three-dimensional geometric shapes embedded in each other would give the ratios of the planets, he believed or hoped, because that would show God's divinity. And he was also an incredible mathematician, and so he was doing all the math to try to show that this was true, and it wouldn't work out. And one of the big problems he had was that they had just really bad data back then. They didn't have a lot of good information about what all these distances actually were. It took, and this picture is not to scale, I hope you know that, this is just pretty. By the way, this picture is taken from Earth Sky, and the site had some nice little discussion about Kepler, and it's worth some reading, I think. But that's where I got these two images from. And there's great stories about Kepler, and some of his peers at the time, a man named Tycho Brahe, had all the good data. So Tycho was this wealthy, eccentric nobleman who paid a bunch of people very little money to just look through these long tubes. They didn't have telescopes, really. They just had these long tubes, and they'd point them at planets and figure out where the planets were and what stars were around them and different times of the year and how far they would move behind the other planets. The word planet means wanderer because the planets change what they're in front of the other stars, and that's where the word planet comes from. But the idea of tracking the planets and seeing where they are over years and could really help you figure out how long it takes for the planet to go around the sun, but also how far away different planets are using an idea called parallax. Anyway, it was very hard to get good data. So Kepler's trying to figure out, all of this, beautiful thing that he believed he needed to find. And he spent years on this. It was basically his life work. And he just didn't have good enough data. And as an astronomer at the time, he knew about Tycho Brahe and Tycho Brahe's data. And Tycho was unwilling to share the data with them. And there's some interesting interplay about how, in the end, Kepler is able to get that data and have finally some data to work on. And he found that he found in the end that he could use ellipses, which is such a simple shape, two-dimensional shape with a simple equation in comparison to all these very complicated things he'd been looking at for years and years. The mathematics he ended up using was actually very clean and simple, and he showed that the period squared for a planet orbiting the sun will be directly proportional to the radius cubed. And he did that before Newton's laws of gravity. He did this using just the data and empirical evidence. So it's a pretty amazing, beautiful thing that he did. And the mathematics is very difficult. We're not doing that. We just want to appreciate this proportionality that he found. But we're going to do it using Kepler's ideas, but using the mathematics of the mathematics that came out of calculus and Newton's laws. So we're going to go after Kepler many years and then use mathematics and ideas that Newton talked about, and then that's backward, right? We can use that and look backwardly to what Kepler did and prove it in seconds. We're going to be able to do it in seconds, even though Kepler took most of his lifetime. And that's because of Newton's law of gravity, helping us to understand what's happening in nature. And to be honest, it's a little more complicated than that, and there's some calculus involved. But you can study about that when you go to college. Right now, we're just going to stick with a very straightforward, assume we have circular orbits and prove that the period squared is proportional to the radius cubed for any orbiting body. Okay, so let's see, I'm going to turn myself off here and we'll go do this proof. We're going to start with the idea that an object that's orbiting the sun is orbiting the sun with a centripetal force acting on it in order to orbit the sun. And that force is the force of gravity. It's the net force on the planet. And so over here, we're going to say that the force of gravity is the net force on the planet from the sun. The net force is centripetal because it's making the planet go around the sun at a constant speed, right? Constantly changing direction. So we know it's accelerating towards the center. And so the value of that centripetal force for anything going in a circle will be mv squared over r. We know that because that's what centripetal force is from 6.1. But now in 6.2, we've learned that the force of gravity is given by this equation, capital GMM over r squared. I just reflexively put d, but that's an r, you can see here. And since Fg is this, which is Fnet, which is Fc, which is this, we can then set this equal to this, which is what we've done up here. Okay, so all this is saying, and if you're doing this proof, they ask this proof for IB, SL a lot, and what you need to start with isn't right here. You want to start with this statement. You want to start with that Fnet is Fc, is this, and that Fnet is also Fg, which is this. Thus, this equals this. And the fact that this equation equals this equation is the beginning of the proof. Okay, so you want to state all of this ahead of time in sentences or in equations, and then you want to write this. Okay, and our first step here, you see that we have one r that can cancel because this is r squared and this is r. Some students feel more comfortable just cross multiplying immediately to have it not be fractions because they hate fractions, but that's fine. I'm okay with fractions, so I'm going to leave things in fractions a little bit. The big substitution you have to be able to do this is, you notice there's no t here. Look at what we're trying to prove. T squared proportional to r cubed, and there's not a t in this thing. So what the heck? What's going on with t? So the idea with getting t is that you have to substitute for v, which is this my also over here. Don't forget that the speed, v is speed, that the speed of any object going around in a circle is going to be given by how far it goes, the circumference, 2 pi r, that's the circumference of a circle, divided by the time it takes to do one circumference, which is exactly what Kepler was interested in, the period of the orbit's planet. How many, he used years, not seconds for his unit, but for us, we'll use seconds. But he used years, and for him, t was how many years does it take for a planet to orbit the sun. For r, Kepler used the distance from the sun to the earth, which is called an astronomical unit. We're going to use meters, okay? But in any case, for Kepler using those units, it's really beautiful to see that this proportionality ends up being in equals, and there's no k at all, that they end up being equals to each other, which is a very cool thing. It has to be true because if you put in Earth, Earth's one of the planets, so for t, if the unit you use was 1 Earth year, and if for r you used 1 astronomical unit, which is 1 Earth radius, then you get 1s for r and 1s for t, and you cube 1, you square 1, you get all 1s, and k equals 1 for the Earth, so k has to be 1 for all the planets. So Kepler sort of understood that by having units that were astronomical type of units, that proportionalities could indeed actually be equivalences. That's not true for us. We're using seconds because we have to, and we're using meters because we have to. So our proportionality constant is going to be more complicated. but we're just going to show that they're proportional, which means we want to have t squared on one side and r cubed on the other, and a bunch of things in there that are constants. I've put a k here to represent them. So we're going to plug in speed, 2 pi r over t. We're going to put that in for v squared, and that's v there, and it's squared. So we have, let me scooch this over, let's turn it off. I think that'll work in the middle of the screencast. We'll see. Anyway, this 2 pi r over t is speed, v, and it's squared, right? If here we've solved for v squared is what I decided to do just to keep that substitution simple. I left it as a fraction. I canceled this 1r, and the m's here canceled. It's interesting to see that this m, sorry, we just had a delivery coming in, but I'm going to keep going because I don't want to have to start over. In any case, this mass here is the mass of the planet. You notice it's in both equations. Where this mass is the mass of the sun, it's only on this equation. Let's review that. Centripetal force. This mass is the mass of the thing that's going in the circle. That'd be the planet. This capital M is the sun. This little m is the mass of the planet. So m is the big thing in the middle. M is the little thing that's going around it. The mass of the little thing going around it cancels. So if we're doing the moon around the earth, this would be the moon, and it would cancel. The earth would still be there. So whatever the big thing in the middle is, stays. The little mass cancels. We plug in for v, 2 pi r over t squared. Okay? So now we're going to get 4. Think about what it'll get, because this square comes into everything. So we're going to get a 4 pi squared r squared over t squared. So that's what this is. Equals, on the other side, you still have g, capital G, universal gravity constant, not the little g. Don't confuse it with gravity field. This is m, the mass of the big, huge thing we're orbiting, usually the sun, divided by r. Now, this r here and this r here is going to be why we get an r cubed. So we take this r, multiply by both sides, or bring it up to this side so we get r cubed. Leave it there. This t squared in the denominator, we're going to bring up and over. And this g and m we're going to bring down. If that's too much for you, just cross multiply and then solve for t squared. But in any case, we get t squared by itself equals, and now we know the proportionality constant k, when you're using standard units, is 4 pi squared over g capital M. And so for orbiting something other than the sun, you can just put in something else. This equation right here is super useful. You're going to use it. Make sure you can derive it. It is not in the IB equation booklet. So you have to be able to do this process pretty quickly and easily. So do it a couple times from scratch. Right now, you should even just see if you can do it from scratch. Look away, blank sheet of paper, nothing on your paper, and see if you can make all the way to this and have it be correct. And if not, then watch this video again and get another blank sheet of paper and try again from scratch. And I think you should even remember these equations, but I suppose you could have your equation booklet if you want to have it to guide you. But from scratch, you should be able to get to this equation without spending a whole lot of time either. Like you that algebra, do it a few times so it becomes sort of habitual, okay? And that is Kepler's third law. You can spend a couple hours on it getting really good at it, but that's nothing compared to the decades that Kepler spent dedicating his entire life to this idea. So suck it up and get it done. How's that for motivational speech? Anyway, my wife's laughing at me right now. Anyway, I hope you're having fun, and you can read about Tycho Brahe, the guy that got all this good data, that eccentric guy I was telling about. If it wasn't for Tycho getting his amazing data, none of this would have happened as quickly, and we're very thankful for Tycho Brahe and his weird eccentric life that made all of this possible, so that Kepler had good numbers to do his amazing mathematics. Anyway, that's it for that one. A little long because of the historical context and stuff. That's pretty cool and pretty important. So I'm glad you're here and that you paid some attention. So thanks so much.